Great. Well, thanks very much. Congratulations, Peter, on the award of your medal. I'm sorry you haven't had the chance to work together. But thanks on behalf of my generation, certainly, for providing the foundations on which we can continue to do some good stuff in the Himalayas and Tibet. So I was asked to give a bit of an overview of the geochronology and the pace of Himalayan tectonics. So Randy nicely provided a title that covered many sins, so I could just pick it up and run with it. So geochronology really underpins everything in earth sciences, from when things happened, how fast things happened, and how long things took. So everything from evolution to rates of tectonics to the start of the solar system and the formation of the Earth. So you've probably all seen these kinds of pictures. So I think that's the formation of the universe at the beginning, and it just spirals all the way up to modern times today. And our understanding of geological time is underpinned by radioactive decay. So unstable parents, of course, produce stable or semi-stable daughters. In case you didn't realize, there's many aspects of modern life that fit in with radioactive decay quite well. So what we do is we take some minerals which incorporate a significant amount of the parent element, parent isotopes. These break down to produce the daughter. And if we can measure the amount of daughter and the amount of parent in our mineral, and we know the half-life, then we can calculate time. So as long as the mineral doesn't incorporate too much of the daughter product as it crystallizes, or at least incorporates it in a way that we can measure it and remove that, then we have some way of understanding at least when the mineral crystallized. So all of this, our understanding of geological time and how old the Earth is, basically goes back to Arthur Holmes. So this is his BSc thesis, okay? This is big stuff here in 1911. He published a paper on the association of lead with uranium in rocks and minerals. And about 2 years later, and we had a big symposium in London last year celebrating this, he published a book on the age, basically hypothesizing the age of the Earth and all these different bits of information that you could put together to understand how old the Earth was and how long it took for different processes to operate. Now, this is well before its time, really, because mass spectrometers hadn't been invented by this point. And Holmes did a lot of his work, really, really detailed chemistry work, trying to basically measure the amounts of lead and the amounts of uranium. So this underpins everything that we now take for granted today. So we can use multiple different minerals and multiple different isotopic decay systems in different minerals to give us different insights into processes that operate at different temperatures. So these kinds of diagrams, again, are quite familiar to most of us. We have temperature across the top, and then different minerals that record different parts of that temperature history. And really simplistically, the higher temperature ones tend to be the chronometers that give us an idea of crystallization, so give us exact periods or pinpoints in time when these minerals crystallized. But lower down, these lower temperature chronometers tend to give us cooling. Now, that's very simplistic, but basically if the daughter product can diffuse out of the mineral, then you're never going to get the timing of crystallization of the mineral if the mineral crystallized at quite high temperatures. So the progress of technology over the last 20 to 30 years has basically meant that we've gone from taking handfuls of crystals and dissolving them up and separating out the lead and uranium laboriously and measuring those to single crystals, and then to the advent of in situ measurement techniques. So even sort of 10, 15 years ago, we had to raster 50 by 50 micron squares in minerals to get enough of both the parent and the daughter elements to measure and get a good, precise and accurate age. And now we're getting to the point where with the laser ablation systems, we can measure 15 micron spots. So these are 15 microns wide and about 10 microns deep. And we can measure, these are monazites, for example, we can measure ages as young as 5 million years or so accurately and precisely. And in fact, we're now getting to the point where with single laser pulses, we can actually get ideas about time. So in minerals such as zircon, where the rims can be really, really thin, and if you have a slice through the mineral, you can't actually date the rim with enough precision because it's too small, you basically stick it onto a piece of double-sided sticky tape. This is work done by John Cottle a few years ago. And just by individual laser pulses, you can actually get ages. So they're not very precise, but they give you an idea. So this is Stacia Gordon's work. She was working in the Canadian Cordillera. And this, just look at this scale. This is 0 to 3.5 microns. And these are different pulses. These are actually SIMS pits rather than laser ablation. But the rim is about 65 million years old, and then suddenly you get through into a core that's nearly 400 million years old. So we've gone over 20 years or so from handfuls of grains to less than a micron. So that's not bad going. So really, the whole point of this is to understand rates and timescales of tectonic processes. So you've all seen these kinds of diagrams where we've got plate spreading and subduction and mountain building processes. And what we really want to understand is which are the really fast processes, the race car processes, and which are the really slow processes, school buses. You know, they trundle along and stop and start and keep going. But these kinds of rates, when we think of them on human timescales, they're still pretty slow. Even the fast processes are about the rates that your fingernails grow. So we're still only talking about 4 or 5 centimeters a year, and these ones are much slower than that. But on geological timescales, of course, over millions of years, that's pretty quick. So metamorphic geologists like to determine pressure-temperature paths. And for some reason, we always plot pressure upwards, even though, of course, pressure increases with depth, and the pressure gives us some idea of burial depth. But that's just the upside-down way it goes. So these kinds of loops get drawn. Pressure tends to increase with depth. Temperature increases as well. And then the rocks start to exhume and then start to cool. And the idea is that we can actually date different points on these paths, and if we can link these different points, different times to different pressure temperature points, we can start building an idea of rates. So these kinds of really steep, high pressure, low temperature loops are associated with subduction and exhumation. And then we get higher temperature, lower pressure loops that tend to be a bit slower, that are linked to collision and exhumation. So if we can determine these pressure temperature paths, determine times on them, and then we can start building up pictures of where material was at different times, how fast burial and exhumation processes took. So you really have to look at the rocks. So we have the big geophysical models, and that's fine, but you really need to get up close and personal with them, especially metamorphic rocks, because these are the ones that record the burial, the recrystallization, the melting, and the exhumation history. And the bigger the hammer, the better sometimes, especially when you're dealing with eclogites, which are pretty hard. So we determine pressure-temperature conditions in different ways. Temperature still tends to be determined by exchange equilibria, so this is the exchange of iron and magnesium in the rock-forming minerals such as biotite and garnet. So the minerals that actually make up the bulk of the rock give us the pressure and temperature information, but time tends to be determined or yielded by the accessory phases. And the trick really is to link the accessory phases and the timing of them into the pressure-temperature loop determined by the rock-forming minerals. So garnet, biotite, for example, give us temperature. Pressure is usually determined by transfer equilibria, so large ions exchanging for smaller, more compact ions as pressure increases, and vice versa. So use barometers such as the garnet aluminium silicate quartz plagioclase barometer. So basically, yeah, the rock-forming minerals give us the pressure-temperature information. Okay, so there are 2 different ways that you can link dates to rates, if you like. First of all, you could use different minerals to give you different parts of the story, and this traditionally has been the way that we've tackled these problems. So minerals such as alunite and garnet tend to give you the timing constraints on the prograde part of the path, so as pressure's increasing and temperature's increasing. Monazite and zircon traditionally give us the timing of the peak pressure-temperature conditions. And then we use minerals such as titanite, rutile, muscovite, biotite. These give us information about the cooling parts of the path, either because that's when they crystallize or because the daughter products tend to diffuse out of the minerals and we only get cooling ages from them. Now, this is all very well and good, but sometimes we end up with a spread of ages. So monazite and zircon especially can crystallize over large tracts of time and large parts of the path. And so as well, if we're trying to link different parts of the path with different decay schemes, we're not always sure that we're comparing like with like. And this is especially a problem when we're dealing with argon-argon dating, which is a whole can of worms, and I won't even go there. But really, you have to be really careful if you're comparing uranium-lead, samarium-neodymium, argon-argon, whatever, different decay schemes to put the rates together. Now, metamorphic chronometers are commonly zoned, zircon and monazite particularly so. And so what we want to try to do is to link the reactions that are forming these minerals into the pressure-temperature path that is gained by the major rock-forming minerals. So really want to try to link the metamorphic ages to metamorphic stages, and that really then helps to tie down the timescales and the rates. So zircon, if we look at these pretty pictures, they're cathodoluminescence images. You can get igneous cores, and then they're overlain by multiple episodes of metamorphic crystallization, if you're lucky. Monazite crystallizes and dissolves and recrystallizes multiple times through a metamorphic cycle, and we can use element maps such as of yttrium and thorium. And if we can date these different zones in these different crystals, then that really helps us to tie down different parts of the path. So the whole idea now is to use these zoned minerals and use the chemistry of the different zones to really start to link in different parts of the path. Because whenever these minerals crystallize, they always leave a fingerprint in the major rock-forming minerals. And if we can understand those fingerprints and unravel them, then we've got a much better chance of much more precisely linking time to where the rock was at that time. So, for example, this monazite might have just crystallized along the decompression part of the path. We might have 3 points here, and it just tells us a very narrow part of the story. All these different zones might have crystallized during the prograde and peak and retrograde parts of the path. So we really have to be quite careful in linking those ages. Otherwise, all we have are dates, and that doesn't necessarily help us. It gives us a time constraint, tells us that this rock is 30 million years old rather than 50 million years old, but we kind of know that already. So really what we're trying to do is understand how and when and where crust is recycled in continental collision zones. We're trying to understand which bits of specifically India and Asia, as they collided, which bits moved really fast, which bits moved really slowly. So I'm going to give 3 quick snapshots into work that's been done by others and work that's been done by my group in the last couple of years. So we've already looked a little bit at the high-pressure rocks in Kurgan today. Going to be looking at those in a little bit more detail. And then moving eastwards to the Jomolari Massif in western Bhutan and the main central thrust zone of Sikkim in India. So just to clue you in, because we've seen different versions of this map today, the Greater Himalayan sequence, the high-grade core of the Himalayas, is in dark green, and it gets wider towards the east. The purple are the Tethyan rocks, which are the oceanic sediments, metasediments, and the yellow are the Lesser Himalayan sequence. So here it is in cross-section. So we have the oceanic crustal rocks sitting on the top, separated by the Greater Himalayan sequence, that high-grade metamorphic core of the Himalaya, with plenty of granites that we've heard about today. That's separated by the South Tibetan detachment. And then the Greater Himalayan sequence is thrust over the Lesser Himalayan sequence, which are very similar compositionally, but much lower grade, by the main central thrust. And then that whole package is thrust over the Siwaliks, which are basically the sediments that were shed off the Himalayas as the Himalayas grew by the main boundary thrust. And that's the thrust that's basically accommodating most of the Himalaya convergence today. So there's the Indian plate, there's the Lesser Himalayan sequence, the Greater Himalayan sequence, the Tethyan sequence, and these domes in Tibet. And the sutures way further back, and so that's Asia, way further back Asian crust way further back in Tibet. So the initial collision between India and Asia, we've had some discussion today about when this happened and what collided with what. But basically, the Indian continental margin subducted beneath Asia or an arc or something, reached ultra-high pressure conditions. There's the pink turning to red here, and then basically exhumed back up towards the surface as that crust, those continental crustal rocks, became weak and detached from the downgoing slab. Now, I don't necessarily think that you need to have slab break off or anything like that. You can continue the subduction, continue the collision, but you do need to detach those high-pressure rocks from whatever the stronger, colder crust is that's dragging them into the mantle in order to allow them to exhume again. So Kagan and Somorari in northwestern India basically show the same kind of cross-sectional structures. You have Asia in the upper plate, you have ophiolites in the suture zone, and you have this plume of ultra-high pressure rocks that have exhumed up in a domal formation right underneath the suture zone with lower grade rocks over the top. So you have normal sense detachments over the top of this dome cored by the highest grade rocks. And again, if we build up these pressure temperature time paths, so together this is work done by a bunch of different people, and we've already seen today that the highest pressures reached by these rocks in Kagan and also in Somorari were basically at coesite bearing pressures. Now, the quartz to coesite transition is instantaneous. Not just geologically instantaneous, but really instantaneous. If you actually put quartz into a high-pressure experiment vessel, take it up to the right pressures and temperatures, it's just a simple locking down of the lattice. And so if you then release the pressure, all the coesite will turn back again into quartz. So in order to actually preserve any coesite in the rock, we need to trap it somehow in a mineral that's actually stronger. So this is an inclusion of coesite in a garnet. That scale bar across the top is about 200 microns. And in fact, you have zircon inside that little nugget of quartz and coesite as well. And what Kaneko et al. Showed was that the coesite was actually included into the zircon. So by dating the zircon at the point where the coesite's included, you're actually dating the timing of the metamorphism where coesite is present. So that's above about 25 kilobars. So if you put all the different bits of information, the timing information together, alunite and zircon both give ages of about 46 million years. So this is either a couple of million years after continental collision, if you believe that continental collision was at 50 million years ago, or a few million years before continental collision, if this was an arc-related collision. But either so, this is actually Indian continental margin that subducted and reached these pressures at this time. Then the rock started to exhume, and we have information from titanite and from rutile only 2 million years later. And these are mid-crustal pressures below about 10 kilobars. So this is real race car tectonics. These are exhumation rates, vertical exhumation rates through the mantle at rates of between 2.5 and 8 centimeters per year. So it's the same vertical rate as normal horizontal plate tectonic rates. And this is about as fast as you get for exhumation processes. Probably mostly buoyancy driven until you get to the mid-crust, and then other processes take over to actually exhume them to the surface. Now we're going to fast forward a few million years to look at what happened to Indian continental crust as collision started and as continental material started to get buried underneath Asia. And this really is a story of stagnation for quite a few millions of years. And I'd put this up here. This is the story of one rock. Okay, so all the information I'm going to be giving you, that Danny Regis, who was postdoc working with me last year, he teased all of this out of one particular rock from the Jomolari Massif, which is in the western area, western Bhutan, just here. So it's Greater Himalayan sequence. It happens to be a little dome that is exposed sort of beneath a clipping of Tethyan sedimentary material on the west. So in order to link age to stage, so these are the ages of accessory phases, which don't tell you much about pressure temperature history, to the stages which are told by the major rock-forming phases, we need to use trace elements, basically, to link the two together. So this is a garnet, this is a calcium map, so it's pretty homogeneous, doesn't really tell you very much. So let's look at the trace elements. So these are the rare earth elements from lanthanum through to lutetium. Divide garnet by chondrite to normalize it. And you get these pretty patterns where you have enrichment in the heavy rare earths and you don't have much in the way of the light rare earths in garnet. So two things just to point out is that from core to rim, so core in the black and rim are in the pale grey here, you have decreasing amounts of the heavy rare earths, and that will become important in a minute. And secondly, if we look at the europium concentrations, we can see there's a minor dip here in the europium. Now, europium is an element that plagioclase adores. So if there's any plagioclase in the rock, it'll soak up as much europium as it can get hold of, which means there isn't very much left for anything else. So whenever there's plagioclase in the rock, you see these negative europium anomalies, so there's less europium than you would expect in all the other minerals. So from core, rim to rim, these are 5 millimeter distances across these garnets. If we look at the europium anomaly, so it's low in the core and then it increases towards the rim of the garnet. So that means that basically there is either more plagioclase or more potassium feldspar around as the garnet rim was crystallizing. Equally, if you look at the phosphorus concentrations, and phosphorus is a trace element in garnet, low concentrations in the core and then increasing towards the mantle and the rim of the garnet. So suggesting that some phosphorus-bearing mineral was dissolving or breaking down. So this could be apatite, for example, or it could be monazite. And monazite's one of our useful chronometer minerals. Now, garnet's really useful for constraining the pressure-temperature conditions, and metamorphic geologists love drawing these really complicated diagrams called pseudosections. You don't need to worry about the details, but basically they're just pressure-temperature diagrams with compositions or mineral assemblages. So you take the fixed composition of the rock, you do a bunch of calculations with them, and it tells you which minerals are present or stable in which field. So each of these different fields gives you a different mineral assemblage. And this is just an example. In this field, plagioclase, garnet, and sillimanite are stable, for example. At high temperatures, melt's present. So what we can do is we can draw these pseudosections for the composition of the rock that was stable as the garnet core was growing, and the composition of the rock that was stable as the garnet rim was growing. And they're slightly different compositions because as garnet grows, it'll lock up some of the mineral chemistry, so they're slightly different compositions. And what we can do is we can plot up the compositions of the garnet in these different sections, and we can see where the core was stable, so the conditions here are about 5 kilobars and about 650 degrees C or so, and the rim was stable at higher pressures and at higher temperatures. So we can see here the garnet was growing along the prograde part of the path as both pressures and temperatures were increasing. So if we now go to monazite, monazite's a cerium phosphate that contains a lot of uranium in its structure. It likes taking in uranium, doesn't like lead very much, so any lead that's in it we can calculate as being broken, coming from the breakdown of the uranium. And we can look at different, these element concentration maps. So this is an yttrium map, there's a core, there's a mantle, and there's a rim. And the rim's really, really thin on these grains, so we couldn't analyze them with the techniques we had to hand, but we managed to get ages from both the core and the rim, and they gave us two really distinct populations. So we have a core that's crystallized 35 million years ago, and a rim that crystallized 21 million years ago. Now, this is quite unusual, actually, for Himalayan rocks to see such a big time difference in monazite, because monazite tends to just dissolve if it gets given the chance to. So we normally tend to get ages between about 18 and 21, or ages between about 38 to 35, but not usually those two different age ranges in the same rock. So that in itself was quite intriguing. And when we collected the rare earth element chemistry from the different monazite zones, so we analysed the monazite core and from the monazite mantle, you can then plot them up against the garnet. So this is monazite over garnet, and these are the rare earth elements again. And there's experimental data from partitioning data that shows what the trend should be if monazite and garnet are in equilibrium. So these open symbols here are the experimental data, and these different lines here are the different either the monazite core with the garnet mantle, or the core with the garnet core, or the monazite mantle with the garnet mantle. And you just plot them all up and see which ones line up with the experimental data. And in this case, the only set that was in equilibrium with each other was the monazite core with the garnet mantle. So basically, that's telling us that the monazite core and the garnet mantle were growing together in equilibrium. So we can put that information together. We can say, okay, the garnet core grew. Then the monazite core grew. At the same time, the garnet mantle was growing, and we know that was 35 million years ago. Then the garnet rim grew. And then we have a monazite mantle which its chemistry tells us was growing in association with melt. It's got a really big europium anomaly. That happened 21 million years ago. And then we know there's a monocyte rim as well, this little rim growing here, but that was at some younger time that we don't have any constraints for at the moment. So we're starting to build up a picture of this one rock, what was going on at different times. Now, zircon in this rock as well. Now, zircon doesn't often crystallize very nicely in Himalayan rocks. It does, but it grows really, really narrow rims that are really difficult to date. But actually, in this rock, the rims were big enough to date. So we have cores which are inherited. They're about 800 million years old and way before Himalayan times. But then we have 3 different rims that we can actually see in cathodoluminescence images. And by really carefully placing the laser spots on these different rims, Danny managed to get ages of 38 million years for the first rim, 35 million years for the second rim, and only one spot on the very outermost rim, because it was really narrow, about roughly 18 million years. Now, in terms of the chemistry, the core, this again is the rare earth element plot that we've seen before, zircon divided by chondrite instead. These are the cores, the dark grey ones, and that's a typical igneous signature. And we know those cores are 800 million years old, so it doesn't have anything to do with Himalayan history. But intriguingly, the rims, the rim 1, which was the widest one, basically just gave this smooth slope, and there's no europium anomaly there at all. Now, that either suggests that plagioclase wasn't present in this rock at all, which suggests eclogite facies conditions, or it suggests that plagioclase was busy reacting away at the same time, and the zircon was managing to take in as much europium as it wanted when it crystallized. So we can start putting all that information together onto one of these pressure-temperature diagrams. So there's the garnet core stability, there's the garnet rim stability, there's the melt stability. We don't really know what this first rim on the zircon means. It's either higher pressure, or it's some lower temperature reaction down here that's producing zircon. But zircon doesn't like crystallizing in the solid state very much, so it's a little bit uncertain as to what this means. But anyway, that was 38 million years ago. Then we have a zircon rim, number 2, with the monocyte core and the garnet mantle crystallizing about 35 million years ago. Then the garnet rim formed, and then the rock started to melt. And we see evidence from both the monazite and the zircon that there's dissolution patterns. So some of those disappeared into the melt. And then monazite started to recrystallize again as the melt recrystallized about 21 million years ago. And then we have a zircon rim that crystallized, well, about 18 million years ago, but that's a bit ropey because there's only one spot. And then we know there's another monazite rim which we have no constraints over in terms of age or pressure temperature conditions. So altogether then, basically that means that something was happening fast, allowing lots of minerals to recrystallize in the rock early on, between 38 and 35 million years ago, and then nothing. We have no information for the next 14 million years, where this rock was, what it was doing. All that we know is that eventually it started to melt, and it started to melt and recrystallize 21 million years ago. So we've got a really slow process happening. But sadly, we don't have any information about how far away it was from the current Himalayan front. All we know is roughly the pressure was somewhere around 8-9 kilobars. And then we suddenly have very rapid activity again later on. But all of these rates, it's all about less than about a centimetre a year. So it's pretty slow compared to the timing of the eclogite exhumation I showed you earlier. But it's just intriguing that this one rock can give you all this history, but you have to unpick it really, really carefully. Do really careful petrology, really careful analytical work. So I now want to move forward in time a little bit to looking at some exhumation processes. This is work that was done by Catherine Mottram, who's submitted her PhD last Monday, so that was very exciting. And she's actually off to the States on a Fulbright scholarship next year, so that's also pretty cool. So she's been working in the main central thrust zone in Sikkim. It's this big re-entrant. And the main central thrust, as we've seen a few times today, basically separates the greater Himalayan sequence from the lesser Himalayan sequence. And it's a really highly deformed, ductile shear zone. In places, it's up to 2 kilometers thick, and basically shows a steady history of deformation, starting at the top and progressively penetrating down towards into the Lesser Himalayan sequence. And at the time when it was operating, sort of 16 to about 10 million years ago, that was the fault that took up most of the deformation in the Himalayas. And that deformation's now jumped forward to the main boundary thrust. So this is what it looks like in map pattern. There's the Greater Himalayan sequence, and there's this big window through into the Lesser Himalayan sequence. And basically there's this big shear zone all the way round the Teesta Valley. And underneath, there's this big duplex of Lesser Himalayan rocks, which is duplexed up and formed this dome. So there's basically an opportunity to look at the timing of the fault on the northern side and the timing of the fault on the southern side. And Catherine hypothesized that if this is all the same fault, that should be a deeper and therefore older bit of the structure now exposed than the bit down here. And that's what actually turned out to be true. There's about sort of 3 to 4 million year difference in timing between the cross-section up here and the cross-section down here. So in the southern part of the exposed dome, garnet, staurolite, biotite, so high-grade metamorphic rocks right underneath the Greater Himalayan sequence. So these are Lesser Himalayan rocks, but high-grade. Basically show monozoic growth from about 21 to about 16 million years. And again, they're nicely zoned, and by carefully picking out different parts of the mineral, the different ages can be teased out. And the northern part of the reentrant, the data are a bit more scattered, but they give an age from about 14.5 to about 11.5 million years old, and this is a few million years younger than the southern part of the section. But actually, this kind of scatter of data can be neatly pulled out in certain samples because the ages can actually be linked to where the monozites sit in the rock. So monozites that sit in the garnet core, they're included in the garnet core, yield an age of about 14.5 million years. Monozites included in the garnet rim give an age of about 13.5 million years. Those in staurolite yield an age of about 12.8, and those in the matrix yield an age of about 11.8. So without doing the really careful petrology and linking where the grains are to the ages, that would have just been a bit of a mess. Because actually each of these grains isn't really zoned, and they're chemically quite similar. But what this shows is that monozites continually recrystallizing all the way through as the rock's crystallizing during the metamorphic cycle. And it's just by chance that they happen to be trapped in some of these different minerals at that particular time. So by teasing that out, it turns a mess into quite an elegant story. Now, that's fine. We know that the rocks in the northern part of that section are about 3 million years older than the rocks in the southern part, but we need to know that we're comparing like with like. So monozites that crystallized at the same part of the pressure-temperature history in one place to be linked to the monozites that crystallized in the same part of the pressure-temperature history in the other place. And then we know we're comparing the same thing, and we can start talking about what that means in terms of rates of movement on the main central thrust. And what Catherine's managed to show with these various trace element fingerprints and careful PT determinations is actually that both the rocks that I've just shown you that she was looking at followed the same pressure-temperature path to within about a kilobar of each other and to within about 50 degrees C. So the rims of the monozites in the southern section, the ones that yielded age of about 16 million years, crystallized at the same bit of the pressure-temperature path as the 12 million year old matrix grains in the northern section. And they are basically somewhere between about 9 kilobars and 7 kilobars at about 650 degrees C. So basically, the rocks that are now exposed in the south went through this part of the path 16 million years ago, and the rocks that are now exposed in the north and exhumed by that doming process reached the same pressure-temperature conditions 12 million years ago. And she's done similar work with lots and lots of different samples. They're all garnet, biotite, staurolite schists all the way around this reentrant. And the rocks in the sort of northeastern part come out at, well, all those parts of that pressure-temperature path come out at about 11 to 12 million years old. Ones in the middle, about 14 million years, and ones in the south here between about 16 to 17. So what Catherine's done is basically plotted up the distance with the age basically along the stretching lineation. So there's about 60 kilometers from her northernmost sample to her southernmost sample along the stretching lineation over the dome. So basically you calculated how far that is, rather than just in a straight line, but up and over the dome. So that's the north-south distance from that sample at the top there. That's the age difference between the sample that she's looking at and that northernmost sample. And basically that gives her a neat slope, gives a thrusting rate of about 9.8 plus or minus 3 millimeters per year, or 10 millimeters per year. So 16 to about 12 million years ago, the main central thrust was moving at 10 millimeters per year. And you can compare that with the amount of deformation that is being accommodated by the main boundary thrust today, which is about 20 millimeters a year. Correct me if I'm wrong, the geophysics
18.
Guys. 18, okay. 18 to 20. So basically today, the 40 millimeters a year of total convergence between India and Asia, 20 millimeters of that, or 18 millimeters of that, is taken up on the main boundary thrust. But 16 to 12 million years ago, that didn't exist, that fault, and the 10 millimeters per year of probably about the same accommodation rate was being taken up on the main central thrust. So by doing this careful pressure, temperature, time, linking age to stage kind of work, you can basically start to unpick which faults were moving when and try to understand which faults were taking up the majority of the deformation at different times in the past. Now, you can do that in many different ways. We saw some that cross-section this morning by Long et al. They used the technique of taking uranium-lead data, comparing it to argon-argon data and fission track data to try to understand changes in rates. I don't know, it's just a different way of doing it by taking the same rocks that have experienced the same pressure-temperature history and using the same mineral to do the dating. It might just give a little bit more of a precise snapshot of what's going on. So in summary then, I've talked a bit about linking metamorphic ages with metamorphic stages, turning metamorphic dates into rates of deformation. And so really by unpicking the burial, the deformation, the recrystallization, and the melting history, linking that with the exhumation history, you can really start to understand what the crust was doing when. So rather than just knowing that rock is 10 million years old and that rock is 50 million years old, it's much more useful to try to unpick the whole pressure, temperature, time path. So as Mike pointed out, we've basically got the full picture of metamorphic history in the Himalayas, metamorphism happening between about 46 million years to 10 million years, and that's fine, but where were the rocks at those times? And I'll leave it at that. Thank you very much.